So our slight detour into black body radiation and temperature of stars is to do with the evidence that we currently have for the Big Bang, and that's to do with our measurement of the temperature of the universe. So the same theory that we just talked about there for stars can be applied to the universe. And so early on in the Big Bang theory, we realised that it must have occurred at really high temperatures, too high that we know matter couldn't currently exist. And so people developed theories for how that temperature would have changed over time, um, and how that developed over time. And that's a kind of full Big Bang theory. It's not just the idea that things started all at a single point. But that gives us two important pieces of evidence that we'll talk about to do with the Big Bang. But first of all, here we've just got a wee kind of demonstration of the different stages. So very early on, basically, we don't know. We can't observe directly what happened. And we don't have a kind of physics for those ridiculously high temperatures that must have existed. But basically, we know it must have cooled down eventually to create what we call quarks, um, electrons, neutrinos, and photons. Now, we'll do more of these in the particle physics chapter next, and learn a wee bit more about them. But these are still in incredibly small timescales before the first kind of matter existed. Then within the first second, we've got things that maybe a bit more familiar with, protons and neutrons. But everything's too energetic to allow the formation of nuclei to join together. And then within the 3 minute stage, then we can actually get protons and neutrons combining to form nuclei. And then eventually electrons can create atoms and so on as well. So it took quite a while for that to happen then, for the atoms to form. So photons are no longer energetic enough to knock electrons out of atoms. So basically, as soon as an electron would bind to an atom in this stage, it would get knocked off by all the background photons flying about. But photons are now free to form what's called cosmic background radiation. And then as we continue, so you can see we're now talking much larger timescales. Eventually, the individual elements, individual atoms can combine together to create stars. Stars can combine together to create galaxies until we get to our present understanding of time. And basically, if we now we'll look at this in a wee bit more detail in a second, but the theory suggests that the cosmic background radiation should now be around about 3 Kelvin. I.e., that's in the microwave region if you look at the corresponding wavelengths. So it's called cosmic microwave background radiation. And we'll talk about our measurements of that in a wee second and what evidence that suggests for the Big Bang theory. But the first bit of evidence we can talk about is known as the helium problem. And basically, we couldn't explain the large abundance of helium in the universe, so we can observe this. There's lots of helium around in the universe, but there's too much for us to be explained just by the formation of stars. But the Big Bang theory itself suggested that helium could be formed directly during the early stages of the Big Bang, and then heavier elements were later created within stars. So, a very simple piece of evidence: the abundance of helium in the universe supports the Big Bang theory. And now, if we look at the cooling down of it, then we can look at the next bit of evidence as well: the cosmic microwave background. So, after basically at the current time, then we should be getting cosmic microwave background radiation. So it was discovered by accident in 1965, before scientists had really developed their theory of it. And basically, people were creating satellites and working in Australia at that point, and they were having problems picking up what they thought was background noise on their satellites. But when they measured this precisely, what they found was one of these curves that we've been studying, black body radiation curves. And when you match that curve to temperatures, then it follows exactly what the theory. There we go. exactly what the theory suggests should be the current temperature of the universe as a whole. So the Big Bang theory, sorry, has got a lot more detail that we don't go into, but part of that detail is this should be the current temperature of the universe. And you can see that the theoretical data from this cosmic microwave background radiation follows that curve exactly. So that's two kind of key pieces of evidence. The most important piece of evidence we obviously have is the fact that the universe is expanding, and that supports the Big Bang theory, so that's Hubble's law and Hubble's data as well. And one last piece of evidence we'll discuss is called Olber's paradox. You don't need to name it as that, but it's basically the idea that the night sky is dark. And that suggests that the universe is finite, because if the universe was infinite, if it spread in all directions, infinitely in all directions, then wherever you looked, there would be stars in that direction, and therefore there shouldn't be black bits in between the stars that we do observe. So that suggests that the universe is finite. Doesn't give you any detail about how it reached there, but it's one more piece of evidence that there is a finite limit to the universe.